So today we'll start new topic, that is states of matter. States of matter. As you know, matter is nothing but anything which occupies space and has a mass. That is called, what you can say, matter. Of course, matter is mainly classified into three types. First type is solid state, second one is liquid state, and third one is what you can say, gaseous state. So like that, these are the important three states of matter what you have to study for our first year PUC level. Okay, so the physical state of matter is what you can say determined by the nature of intermolecular forces and the effect of thermal energy. So here let us will come to know what are intermolecular forces and what is thermal energy and what relationship is there between intermolecular forces and thermal energy. Let us will see in this topic. So here intermolecular forces. Intermolecular forces. So here intermolecular forces are nothing but attractive forces or repulsive forces. Both we can say attractive, the attractive or repulsive forces that are operating between interacting atoms and molecules are known as intermolecular forces. So here intermolecular forces are nothing but what you can say. So these are attractive or repulsive forces that are operating between interacting atoms or molecules, you can say. So here there are several types of intermolecular forces as you have studied here. So here next types of what you can say, types of intermolecular forces. So here we have to study these types of intermolecular forces. So there are three types in intermolecular forces. Three types of intermolecular forces. One is dispersion forces or London forces. Second one is dipole forces, and third one is induced dipole forces. So of course here the first one is dispersion forces or London forces. Involves forces between non-polar molecules. This dipole, what you can say, dispersion forces or London forces. That London forces, the invented person, he is from England, London, Fridge London. Sorry, his name is Fridge London. So that is why this force, the name of this force is given, his name only, London forces. This involves forces between non-polar molecules. So, second one is dipole-dipole forces. Second one is dipole-dipole forces. So, here one can see here dipole-dipole forces between, what you can say, two dipole molecules. For example, hydrogen chloride molecule is there, HCl molecule. So, here the forces between two hydrogen chloride molecules, because hydrogen chloride molecule is a, what you can say, polar molecule. So, the polarity creates between hydrogen and chlorine atoms, because hydrogen is a electropositive atom and chlorine is electronegative element. So that is why, so the force between two polar molecules results dipole-dipole forces, you can say. So here, third one, dipole-induced dipole forces. So here one is what you can say, dipole, that molecule, polar molecule, and what you can say, another induced polar molecule. The force of attraction between polar and induced dipole molecule, that involves dipole, induced dipole forces. The second one, what you have seen, dipole-dipole forces involves two polar molecules, for example, HCl. So this is what you can say, three types of intermolecular forces. So we have seen, after saying that intermolecular forces, let us, so this what you can say, the intermolecular forces, and one more, that thermal energy. Let us see thermal energy, then we will go for what you can say. So, thermal energy versus dipole. So, here thermal energy, after seeing intermolecular forces, next one is thermal energy. So, here thermal energy, we can see the energy of a body which arises from motion of atoms or molecules, you can say. When atoms or molecules starts to move, so this energy, what you can say, arises. The thermal energy is an energy which arises when atoms or molecules are in motion. So let it be here. We can see here, one should remember that thermal energy keeps particles away from one another. So it means when molecules or atoms are in motion, naturally this thermal energy, what you can say, it keeps atoms and molecules away from each other. And here thermal energy, one more point, thermal energy is directly proportional to the absolute temperature of the substance. So like that, here we have seen 3 points regarding thermal energy. The first point is what is known as thermal energy. It is nothing but energy of a body arising from motion of particles, that is a motion of its atoms or molecules. Secondly, thermal energy is directly proportional to the absolute temperature of the substance. And the third point of thermal energy is that, so one should remember that thermal energy keeps the particles away from one another. So here, after saying thermal energy, regarding thermal energy, next what you can say, intermolecular forces versus thermal energy. Intermolecular forces and thermal energy. So here, intermolecular forces, intermolecular forces versus intermolecular forces versus thermal energy. So here, if intermolecular forces, already we know that what are intermolecular forces, which tend to keep the molecules together. So here, anybody can say that intermolecular forces always keeps atoms or molecules in its atoms or molecules keeps together. Which one? Intermolecular forces. Whereas thermal energy keeps its atoms or molecules far away from each other. See how the difference is there between intermolecular forces and thermal energy. Intermolecular forces keeps atoms and molecules together, whereas thermal energy keeps atoms and molecules far away from each other. So this is the difference, what you can say, between intermolecular forces and thermal energy. So here, if what you can say, thermal energy predominates over thermal energy, if intermolecular forces predominates over thermal energy, it results solid state. So if it becomes reverse, that means if thermal energy predominates intermolecular forces, then the state of matter will be gaseous state. And the third one is, if the intermolecular forces and thermal energy are comparable, then it results liquid state. See how it is interesting. So thermal energy, intermolecular forces and thermal energy, what you can say, intermolecular forces versus thermal energy, that means it decides the state of matter. So for solid state, intermolecular forces dominates over thermal energy, and for gaseous state, thermal energy predominates or dominates over intermolecular forces. And the third one, so what you can say, liquid state of matter arises when intermolecular forces and thermal energy are comparable with each other. So this is what you can say. So for intermolecular forces versus thermal energy. So after saying this intermolecular forces and thermal energy relationship, then we have to see next of this topic, that is important, gaseous state. Gaseous state. We'll see now gaseous state. So as you know, gaseous state is one of the part of what you can say physical state of matter. One of the part of physical state of the matter. So just now we have seen how these three physical states arises, that intermolecular forces versus thermal energy. When we have seen the relationship between these two, intermolecular forces and thermal energy. So this gaseous state arises when thermal energy predominates intermolecular forces. Then it arises. This gaseous state arises. Let it be. So here one should see some characteristic physical properties of gases, you can say. When you are studying gaseous state, one should see here what the important physical properties or important characteristic physical properties of gases. So here he is giving introduction for gaseous state, that gaseous state is the simplest state of matter. And secondly, if we observe modern periodic table, so we can see only 11 naturally occurring gases. So under the normal conditions of temperature and pressure, when we observe periodic table, we can find only 11 elements are in the gaseous state. So you may ask, which are those 11 elements? So hydrogen and helium, and next nitrogen, oxygen. So total 4, and fluorine, that is halogens, and chlorine, these two, 6, and these inert gases, that is the 18th group elements. What are those? So these are 5: helium, neon, argon, krypton, xenon, radon. So total these are what you can say 11 elements in the periodic table, which are really gas in the gaseous state under normal conditions. Let it be. So here one has to study the some important characteristic properties of what you can say gases. So here gases, as you know, entirely different from solid and liquid state, especially in its what you can say shape. The shape of gas we cannot say perfectly, because the gas occupies the space. The shape of gas, we can say the shape of gas, no guarantee. It means which occupies the volume of gas, that which occupies the container. If a cylindrical shape is there, so we can say shape of gas is cylindrical. If a rectangular shape of container is there, we can say shape of gas is rectangular. That is why we cannot say the shape of gas. So that is why we can say gases have neither definite volume nor definite shape. Gases, what you can say, assume volume and shape of the container. Just we have seen there is no definite shape and what you can say volume for a gaseous state, gases. Secondly, the second important characteristic property is that gases are highly compressible. See, gases are highly compressible. So, not expandable, compressible. And thirdly, gases exert pressure equally in all directions. See, if gas is taken in a container, a cube or any container, so what he is telling, gases, the pressure exerted by gas is equal in all directions, he is telling. So, and the fourth characteristic property is that gases have much less density than the solids and liquids. Regarding density of gases he is talking is that, so gases will possess low density or smaller density or less density compared to solid state and liquid state. And the fifth characteristic property of gases is that gases have large intermolecular spaces. See here. So, gases have a large intermolecular spaces. Its meaning is that, so gas molecules with one another will have more space. If we are taken in a container, so he is telling that have large intermolecular spaces. So the sixth characteristic property of gases is that gases diffuse easily or intermix completely. Gases diffusion. As far as diffusion is concerned, diffuse easily and mix with another gas very easily. Intermix completely in all proportions without any, what you can say, mechanical aid. So these gases do not take any help for mixing with other gases. So it means intermix completely with another gases in all proportions without taking any other help, or what you can say, which type of help? Mechanical aid. Aid means help. Without taking any mechanical aid, these gases can intermix completely in all proportions without any help. So these are just, we have seen 6, what you can say, characteristic properties of gases. So now we will come to another important aspect of this topic is that gas laws. Just we have to go through now gas laws. After seeing these properties of gaseous state, now we will go for gas laws. Okay. So here a very interesting aspect of gas laws. So here the gaseous state, the state of gaseous system is described by 4 measurable properties. The state of a gaseous system is best described by 4 measurable properties. The first property is that pressure. Pressure is a first property of what to explain, to describe these properties. Pressure, first one. Second one is a volume, second property, measurable property. And third one is a temperature. Third one is temperature. And last one is amount. Amount means that is the amount of substance or amount. So here pressure, as you know, it is denoted by capital P. Volume can be denoted by capital V. And temperature can be denoted by capital T. And the amount or amount of substance is denoted by what you can say, small m. This m is what you can say, amount. This is what you can say, fourth property. So third one is a temperature T, and second one is a volume capital V, and the first one is a pressure. So like that capital P. So these are the four: pressure P, volume P, and temperature T, and amount, that is a M. So these are the four measurable properties of a gaseous system. So see here, the quantitative relationship among these four properties, it leads to some gas laws. So the quantitative, what is telling? The quantitative relationship between these four measurable properties leads to some gas laws. So the gas laws arises due to the relationship between these four measurable properties. So let us study what are those gas laws. So here first we'll see total four gas laws we have to study for PUC first year level. So we'll study one by one those. So here the first one is what you can say, Boyles Law. There are four gas laws we have to study. First one is Boyles Law, and the second one is Charles Law, and the third one is what you can say, third one is so Gay-Lussac's Law. Gay, G-A-Y, Gay-Lussac's Law, and the fourth one is what you can say, Avogadro Law. See, so we have to study for PUC first year level how many gas laws? Boyles Law, Charles Law, then Gay-Lussac's Law, and the fourth one is Avogadro Law. So we'll see one by one the statement and mathematical statements. Now the first one we'll study in detail about here Boyles Law. So Robert Boyle just studied the properties of gases and came to his conclusion called his law of statement. So here let us see first statement of Boyles Law. So here Boyles Law states that at a constant temperature, the pressure of a gas is inversely proportional to its volume. See, once again you listen that Boyles Law statement. At a constant temperature remains constant, the pressure of a gas, given mass of a gas, the pressure of a given mass of a gas is inversely proportional to its volume. Inversely proportional to its volume. So this is what you can say statement of Boyles Law. How we can state Boyles Law? Boyles Law states that at constant temperature the pressure of a given mass of a gas is inversely proportional to its volume. So here mathematically one can stated as pressure of a gas is inversely proportional to volume, its volume. If T temperature is constant. So this is what I can say mathematical statement for Boyles Law. Pressure is inversely proportional to what you can say volume of the gas. So this we can simplify, or P we can remove this proportionality constant as given and into 1 by V. So this is also there, or PV, if you cross multiply, if you take cross multiplication, PV is equal to here where K1 is called proportionality constant. Proportionality constant. So therefore PV is equal to, if you go for a class multiplication, you can write a constant. So this is what you can say mathematical statement of Boyles Law. PV is equal to constant, we can say. Here PV is equal to constant if or when T is a constant. So this is what you can say mathematical statement for Boyles Law. So here after seeing Boyles Law, next we'll go for Charles Law. So here Charles Law, second one we'll see Charles Law. Okay, second one. Charles Law. So here Charles, scientist, studied the properties of gases and came to conclusion to give his statement. So here this law, that Charles law, states that at constant pressure, the volume of fixed mass of a gas, is directly proportional to its absolute temperature. See, very interesting. So just now we have seen Boyles law. That is inversely proportional. What is inversely proportional? Pressure is inversely proportional to its volume. Whereas in Charles law, we are saying their temperature is constant in Boyles law. Whereas here in Charles law, pressure remains constant. The volume of a fixed mass of a gas is directly proportional to its absolute temperature or absolute temperature of the gas. So that means once again you listen the statement of Charles law. Charles law states that at constant pressure, see, you should not confuse, at constant pressure the volume of a fixed mass of a gas is directly, there inversely, here directly proportional to the absolute temperature of the gas. So this is what you can say statement of Charles law. Mathematically, this law, the Charles law is stated as so volume of fixed mass of the gas is directly proportional to temperature, absolute temperature, if pressure is constant. So here or V is equal to, if you remove proportionality sign, you can write a constant, that is a K2 into T, where K2 is called, what you can say, proportionality constant. K2 is called a proportionality constant, or we can write V is equal to, or V by T, we can take T this side, V by T is equal to constant. V by T is equal to, V by T is equal to constant. So this is what we can say mathematical statement for Charles law, that PV is equal to constant, mathematical statement for Boyles law, whereas V by T is equal to constant is a mathematical statement for what you can say Charles law. So after saying the Charles law, next we will go for what you can say one more law, that is Gay-Lussac's law. Third one, Gay-Lussac's law. Third one, Gay-Lussac's law. Gay-Lussac's law. Person name is like that. Gay, G-A-Y, Gay. Lussac, L-U-S-S-A-C, Lussac, first of Lussac's law. So here, Gay-Lussac studied the properties of what you can say gases and came to conclusion to give his statement. So here, just now we have seen that in Boyles law, temperature remains constant. Whereas in Charles law, pressure remains constant. Whereas in Gay-Lussac's law, we have to see here volume remains constant. See, very interesting. In Boyles law, temperature was constant, and in Charles law, pressure is a constant. Whereas in Gay-Lussac's law, have to observe that volume of the gas remains constant. So this law states that at constant volume, the pressure of a fixed mass of gas, or the fixed amount of gas, the pressure of a fixed amount of a gas is directly proportional to the temperature. See, pressure directly proportional to temperature when volume is kept constant. So this is what you can say Gay-Lussac's law. So once again, statement of Gay-Lussac's law is that at a constant volume, the pressure of a fixed mass of gas or fixed amount of a gas is directly, see, in Charles law we have seen directly. So here also, pressure of a fixed amount of a gas is directly proportional to the temperature. That is, mathematically one can write pressure of a gas or fixed amount of a gas is directly proportional to its temperature. So this is the what you can say when if V volume is constant. Very interesting. So in Boyles law, temperature T was constant. In Charles law, P pressure was constant, and here Gay-Lussac's law V is a constant. Don't confuse between these three laws. So Boyles law inversely proportional, whereas Charles law directly proportional. Similarly, Gaseous law is also directly proportional. They are just pressure and temperature relationship. This is a pressure-temperature relationship, whereas Charles law temperature and volume relationship, whereas the Boyles law is what you can say pressure and volume relationship. Pressure and volume relationship, Boyles law. Temperature and volume relationship, Charles law. And this one is pressure and temperature relationship. Let it be here that P is a pressure of a fixed mass, fixed amount of gas is directly proportional to T if volume is kept constant. This is what you can say statement, mathematical statement of Gaseous law. If you simplify this, or P is equal to K3 into T, where what you can say K3 is proportionality constant, and or even we can write P by T. P by T is equal to constant. So this is what you can say mathematical statement of Gaseous law. P by T, Boyles law, PV is equal to constant, whereas Charles law, V by T is equal to constant, and Gaseous law is P by T. P by T is equal to constant. So this is what you can say Gaseous law. And the fourth law is gas law is Avogadro's law. We'll see here in Avogadro's law, volume and amount of gas, volume and amount of gas relationship we have to see. Volume and amount of gas you can see. The fourth one is here, what you can say? Which one that the fourth one? Avogadro. AVO GADRO. Avogadro law. So this Avogadro is a person name. So he studied about properties of gases and came to conclusion in the form of his statement. So here this one is volume and amount of gas relationship is there between these. In this Avogadro law, we are seeing the relationship between volume and amount of gas. So let it be here statement for this Avogadro law. Just very easy, interesting. So this law states that, Avogadro's law states that under similar conditions of temperature and pressure, or under the same conditions of temperature and pressure, all gases, means equal volumes of all gases contain equal number of molecules. Very interesting. This law, Avogadro law, states that equal volumes of all gases, under the same conditions of temperature and pressure, temperature and pressure should be same. Under that condition, what you can say? So those equal volumes of gases contain same number of molecules. So this is what you can say Avogadro law statement. So mathematically Avogadro's law states that volume, that is a V, is directly proportional to M. So here, if V and T are kept constant. So what is studying? Under the same conditions of temperature and pressure, or pressure and temperature, the equal volumes of all gases, under the same conditions of pressure and temperature, or temperature and pressure, contain equal number of molecules. That is, how much volume of gas is there, that much same number, all gas. You can take any example, nitrogen gas you can take, hydrogen gas you can take, helium gas you can take. The atomic masses of these gases are different, but when you are taking equal volumes, in volume, if the all gases are equal and contain equal number of molecules in the gas, that is what you can say Avogadro's law. So this is simplified as V is equal to K4 into N. So K4N, here K4 is called, what you can say, proportionality constant. So if you simplify this, so what do we get? Finally, V is equal to, that is K4N, where K4 is constant. So here, this is what you can say, mathematical statement for Avogadro's law. V is equal to K4 into N. So here, the number of gas molecules in 1 mole, the number of molecules in 1 mole of a gas has been determined to be 6.022 into 10 to the power 23. See here, 6.022 into 10 to the power 23 is a number of molecules in the 1 mole of a gas. That 1 mole of a gas, 1 molecule of gas, or 1 number of molecules in 1 mole of a gas is how much? That is 6.022 into 10 to the power 23. This constant is known as Avogadro's constant.